Welcome to session 5 of the SolidityATL Intro to Web3 Security course. From this session on through the end, our focus will now be 100% on the security aspect of smart contracts from the perspective of a security researcher, but also as a developer as well. Homeworks moving forward will have a very strong emphasis on CTFs, specifically around the vulnerabilities that we discuss. Every session from here on out will be diving deep into at least a couple of vulnerabilities. And even if you just become comfortable and familiar with one or two different vulnerability types, you could use that knowledge to find real vulnerabilities in audits. So I want you to keep in mind while going through this lesson to start building a mental database of vulnerabilities or attack vectors, as these are the things that you will be looking for during an audit. The agenda for this lesson includes, first we're going to talk about code comprehension. And by code comprehension, that means understanding what a protocol's code is doing in a systematic way. There's different mental models and approaches for how to go about code comprehension. So we're going to talk about the approaches that we take, and also mention some other auditor approaches as well. Next, we're going to talk about some of the most common vulnerabilities and attack vectors in Web3 hacks. Most hacks that occur fall under a category of 10 to 20 different attack vectors. We're going to be talking about some of them from a high level in Module 2. The next third module, we're going to talk about how protocols can defend themselves. So the different ways that protocols and protocol developers can minimize the risk of being hacked and also have a way to minimize the impact of hacks if they occur. And the last module, we're going to deep dive into a couple of vulnerabilities, specifically re-entrancy and logic errors around incorrect math. The first module of this lesson, we'll be going through the concept of code comprehension and some of the things that we do to systematically come into a new code base and build up a understanding well enough to find vulnerabilities. Now, this is not necessarily a complete list of all the things that you could do to help comprehend code, but I feel like it's a good starting place that covers a lot of the activities you will be doing. At the end of this module, we're going to be demoing some of these tactics with Uniswap's code base to help reinforce these concepts and show what these actually look like. Just to be explicit about the tactics here we're going to cover, we're going to go through threat modeling, what that is and how it's useful, reading code, specifically how to systematically approach a code base to be able to understand how it works. Then we're going to talk about function mapping and tracing, which is a subset of reading code, but there's multiple ways to do it. And being able to trace functions inside of smart contracts can help you really understand the code and find medium and high vulnerabilities. Then we're going to talk about where documentation comes into this. So protocols usually write documentation. So how to use that to your advantage. Then we're going to walk through testing, specifically like unit tests, integration tests, manual testing with on-chain data, and also writing proof of concepts and why that's very powerful and not just understanding the code, but finding vulnerabilities. And then lastly, we're going to go through the importance of note taking and some ways to actually take notes that we use. The first tactic we're going to talk about when it comes to code comprehension is reading documentation. It's important because it helps you understand what developer assumptions are. It gives you an idea of how the developers intend for the protocol to work. And one really important thing to note is just because something is written in the documentation doesn't mean that's how the code actually works. So the two things you get from reading documentation is one, a better understanding of the protocol and what the intended or expected behavior is. And two, you as a both developer and security researcher, you want to make sure the documentation correctly reflects what the smart contract code is doing. During the process of an audit, it's very important to read through the documentation if there is documentation provided to help you gain a better understanding of the protocol. There's many different processes for reading documentation that you can go through, but we'll show you what we do once we start looking at Uniswap code. One mindset I always have when I'm reading documents is I never assume that what the documentation says is what's actually happening until I confirm it myself by looking at the code. Because I think in most of the audits that I've done, there have been mistakes in the documentation that needs to be corrected. I also usually go through the documentation multiple times throughout the audit at different points. And there are also some protocols that don't have any documentation, which can be a red flag, as that can make an audit a lot more difficult if you're just going based on code and you don't have any documentation to go with. The next tactic we're going to talk about for code comprehension is one of the most important, and that's reading the code. I like to think of it similar to what developers do during a code review, where you're trying to understand what the code is doing while also trying to build a mental model so that as you go through the code multiple times, you start to understand what the protocol is doing, what functionality is going on. The code is a source of truth. So as I mentioned, documentation can say whatever it wants, but at the end of the day, the code is what's being executed. And being able to efficiently read and comprehend code will help you improve your understanding of a protocol. The goal when you're reading code is understanding what the code is actually doing, building a mental model of that protocol, and starting to get an understanding of what areas an attacker might look for. So that's understanding state transitions, external calls, those type of things. Generally, during an audit, I read through a code base multiple times with many different ways of reading it. So I may be reading it just to try and understand. I may be reading it to look for code smells. So there could be a situation where I've read through the code base once or twice, have a general understanding of what's happening. Now I'm looking for specific code smells of code that just doesn't look quite right. The next tactic we're going to talk through for code comprehension actually falls under a subset of reading code, and that is function mapping and function tracing. So before going into this, I want to introduce the concept, if you're not familiar, of a state machine. So state machine is something in computer science and programming in general, whether it be with Web2 programming or robotics or whatever type of programming there is, to be able to visualize, given a starting state of the program, how that program will evolve over time based on user input. So here I'm showing a very simple state machine where you can see there is a start to the program, and each of these nodes or circles here is essentially telling you the state of what the program is currently doing. And each arrow is a state transition. So you can imagine if this was just a normal Web2 program, a function calling into some code with start, making, and initially the state of that program could be, hey, it's not started. So some external call comes and starts it. And in order to transition to the loading state, the program will then potentially fetch some data. And so now the state of that program is loading. And based upon the response, if it, say, gets an error, then the program will move into an error state. Or if the response is successful, then the program moves to the success state. And you can see this program here can only have 4 states, and the state transitions are how you move back and forth between the states. With function mapping inside of a smart contract, you're essentially trying to do the same thing, not necessarily drawing out that state machine model in that fashion, but you're trying to understand what are all the states that this smart contract can be in, and what are the different transitions between those states. For simpler protocols, say you're only auditing a protocol with one smart contract, the function mapping could be relatively simple because it's all contained within that one contract. But a lot of protocols will have multiple smart contracts that interact with each other. And so the purpose of function mapping and tracing is to have a clear understanding of, given this input into this function, here is how the program will execute, whether it be making external function calls and continuing to go through the trace there, or staying within the same contract and changing a bunch of state. So this is a very crucial skill to learn how to do, to be able to find the higher impact vulnerabilities, because through this function mapping or tracing, you're able to really understand what's happening in the code. And once you have that understanding, you can start to think of ways you can tweak, or you can use that understanding to hack the smart contract. Another purpose of this function mapping is to identify where external calls occur, because external calls, so contracts calling other contracts, are something you want to be looking for, because a lot of vulnerabilities tend to be with contract interactions. And the last point for the purpose of function mapping is being able to narrow your scope in. Say you're only trying to map a single function, or you want to map an entire user flow. So say someone is, depositing funds into a pool and then receiving some rewards, and then, staking those rewards for some other thing. So being able to narrow in your scope on like a single function versus an entire user flow is a very helpful skill. Main goals here are build a mental model of the protocol. So this is how one way you can help really solidify your understanding, but also identify attack surfaces and potential bugs. And attack surfaces are just what areas of the code can you poke with certain data to exploit. The next tactic for code comprehension we're going to talk through is threat modeling. And this is something that exists in the Web2 or traditional software security space. where this helps, the purpose of threat modeling is to help you visualize all the moving pieces of a protocol and what potential threats you can identify before actually doing a deep dive in the code. So a threat model can be something you write down in words, but it can also be visual. Um, some of the goals with threat models is you want to understand all the different actors in a protocol. So there could be users, there could be admins, there could be liquidity providers, all with access to different methods in a contract with different levels of trust assumptions. So when you're creating a threat model, what you're trying to do is understand what functions can be called by anybody, what functions are gated behind specific roles, and what trust assumptions are you having with those trusted parties. For example, is it possible for the admin of a particular smart contract to drain all the user funds inside of that contract? Those are the type of things that you're trying to look for in a threat model. Generally, I'll do a combination of writing a threat model down with words, but I also am a visual learner and I like to draw pictures. So I want to show an example from one of the top security researchers in the world, on what some of his threat models look like. And I really like them because they're relatively simple and easy to digest. And I think they do a great job in showing what the goal is in a threat model. So we're going to be looking at a security review from Pashov. If you're not familiar with Pashov, he's one of the top security researchers in the world. And so what we're looking at is one of his audit reports. And I want you to pay attention specifically to the observations and the privilege roles and actors. And so what this is doing is this is a threat model showing here are the different parties inside of this protocol. And generally these are based on roles. So there's, I haven't looked at this protocol, but you can see there's, different roles for governance. There's a different role for operating a pool, and each of these roles can do different things. And so you can see written out in words, here's this role, a pool owner, and the pool owner can set withdrawals and do other things. So this is a relatively simple threat model for this protocol. And it not only helps you as the security researcher by writing it down to reinforce it, but it's also very easy to take this and then share it with the protocol themselves or other security researchers to help them come up to speed on a code base more quickly. So this is a great example of what a threat model with words looks like. The next tactic for code comprehension that we're going to talk about, I think, is one of the most important. And this is something that can help you advance from a beginner security researcher to intermediate level. And that's test and proof of concepts. So from the protocols perspective, generally protocols will write unit tests and integration tests to validate the function of their smart contract. And so reading their existing test can help you understand the protocol better and understand the intended uses of the protocol. In conjunction with the documentation, because I view tests similar to documentation, where it just shows you, it helps you understand the code a lot faster. And it also shows you what the developers are assuming, like what inputs come into certain functions and how the protocol will be used. With that, um, getting in the habit of doing an audit with the protocol with tests, writing test on top of the existing test so you can poke and prod at the protocol is a very handy tool for finding and validating findings. This third point, for the purpose of writing proof of concepts to take ambiguity away, is something that I think is very important to be able to have like 100% confidence that an issue is really there, and then to be able to show a protocol not only the issue is there, but how they can fix it. And then if you have a proof of concept that actually is a vulnerability, the protocol can add that to their test suite so they can just test for it and not have that issue again. I generally strive to write proof of concepts for high and critical vulnerabilities and some mediums as well. And more often than not, I will either confirm that vulnerability or confirm it doesn't exist. And so that saves me a lot of time from wondering like, is this actually a vulnerability? Just writing a proof of concept test can take away all the ambiguity. One thing to note, there are some protocols that don't have good test coverage or any test coverage at all. So if you're auditing a protocol that does not have any tests, generally I take that as a sign that there's going to be a lot of bugs there. So if you're auditing a protocol that doesn't have a lot of tests, I think it is worth it to, set up Foundry or set up Hardhat to start writing those tests and validating findings because there's a higher likelihood they're there. This fourth point here, we didn't talk about forking yet, but some protocols that you may encounter when auditing are actually already live and they could be just adding functionality. So another form of test and writing proof of concepts is actually forking that protocol from whatever mainnet they're deployed on to your local testnet. And that will give you real data of how the protocol actually exists to write your tests against. And sometimes that can be a lot faster than trying to set up a specific environment for validating your test. Now, the goals for writing tests for a protocol are generally having higher test coverage means the code is more secure, and they're wanting to validate the functionality of a contract. From a security researcher, the tests are additional documentation to help you understand the protocol, but also you being comfortable writing tests can help you gain a better understanding of the protocol faster and also validate any issues that you think you found, especially the higher severity issues. The next tactic around code comprehension we're going to talk about, I also think is very important, is taking notes. So why is note taking important? One, it helps you build your mental model of what the code is doing and how the protocol operates, because the act of writing it down, whether you're using pen to paper, note taking software, whiteboard, or audit tags, reinforces those ideas in your head. And secondly, it makes it so you don't have to keep all the information in your head and try and remember that throughout the audit. It just helps you cache all the important information that you have. If you're working in a team, having good notes can also help you easily transfer the knowledge and ideas to help bring them up to speed so that you'll have more time to have deep focus on trying to find vulnerabilities versus understanding the protocol. Some of the goals that I generally have with note taking are documenting any questions or ideas that I have around the protocol that I may want to explore later, making sure that I have a understanding of what the protocol is doing. So sometimes I will say go through a function trace where I'm looking through, a smart contract function that's calling another smart contract, and there's a bunch of stuff going on. I will write out what that's doing with words, and that really helps me reinforce what's going on. The second point helps minimize memorization. I don't like to rely on my memorization when I'm auditing, because there could be a lot of information to keep. And the third point is it's easier to get into a flow state when you don't have to hold as much in your head. So for myself, whenever I'm auditing, I regularly read through my notes. And before starting a deep dive, I like to prime myself with my notes. And that generally makes it easier for me to get into a good flow state for focusing on an audit. The last tactic I really like for code comprehension that I did not mention at the start of this module is talking with the protocol devs. A lot of the times during an audit, there will be points where you will have questions or ideas of how you think the protocol works or the possibility of a vulnerability, but you're not 100% certain. Having a good communication channel with developers who wrote that protocol can help you clarify those questions and ideas, and also can help you save a lot of time during the audit, because the people who wrote the code will have the best understanding of what it's doing and the intent. And asking them directly, hey, is this an issue, or is my idea about what you're doing with this protocol in this way correct, can help you save a lot of time, where developers can be like, oh yeah, that is an issue, thanks for bringing it up. And you're like, okay, I'll add that to report. Or no, this is intended behavior and we mitigate it because of X, Y, and Z. Like if a protocol team's like, oh, that's not an issue because we have a multi-sig wallet, for example, but that's not something you would be aware of just by looking at the code. So it's very powerful to have a constant stream of communication with the protocol developers. And that also helps you maintain a good relationship with them during the security review. Some of the goals when you're talking to the developers during an audit are validating some ideas you have on potential attack vectors or potential architectural things. Because sometimes if you think that the way a protocol architected their code can be improved, that's something the developers would also like to hear. Second point, you can also get clarification on protocol functionality and what's intended. And the third point there is you're more efficient with your time. So by asking developers questions and keeping engaged with them versus spending hours alone wondering, trying to figure out the answer to a question, you may be able to save yourself a lot of time to focus on other areas of the code. So it's very important to have a path of communication with developers.
So in this demo, we're going to do a simple exercise for how we do a simple threat model. As Robert mentioned, there are many different ways that people approach threat models. So what we're going to try to do is do a compressed threat model exercise, hopefully in 5 minutes or less. So what we're going to choose is a project. We're going to use Uniswap's V3. I've already created an example threat model directory. So we're going to see how I would approach a threat model. If I had 5 minutes, of course, it'd be a lot more flushed out. But at this point in time, we're going to do a simple threat model of Uniswap V3. First thing you might want to do is get the draw.io integration / extension. This is the one I have. It's amazing for doing draw.io diagrams within VS Code. For those of you who are not familiar, draw.io is a simple way to create flowcharts from your device. So let's go ahead and set up this draw.io. We're going to create a new file and example.draw.io or draw.io. I can't remember if this is the, yes, okay. and we're going to do it for Uniswap. So when doing a threat model, there's a few things you want. You're going to want let's see if there's a better way to describe this. Can I do bullets? Let's just do a square. Okay. Yeah. All right, so you're gonna have an actors table, and let's think of first. Let's look at. Honestly, I messed up. Let's actually do text, since we want our diagram to represent different parts of the Uniswap code. All right, so let's do actors. So you're gonna have an actors table or section. You may have an assets section, and that's all we're really gonna do for now. And also we can do attack vectors. Again, this would be way more flushed out if you were doing this, and it'd be a lot prettier, but like I said, we're doing a simple one. And then on this side of the page, we're going to do the actual threat model itself. So these are going to be like the supporting documentation, or like the supporting attributes for your threat model, and then we're going to have our visual piece, which is the threat model. So let's take a quick look. We're going to do Uniswap v3. Wish I knew I was on time. Maybe a little bit longer than 5 minutes, but that is okay. All right, so let's just take a look. This is what I would typically do. I may look at a small blog or just some documentation on what Uniswap v3 is. Obviously, if you haven't looked at Uniswap v1, you should probably start there. But we're going to look at v3. Okay, so the most flexible and efficient AMM. LPs can provide liquidity, capital efficiency, LPs can say increase. Okay, so LPs are liquidity providers. That's an actor. You're going to have your users who are performing swaps. You can have an attacker as another actor. Who else? Developers. So that's who are going to be our main actors in this diagram. And we're just looking at some of the key components of Uniswap v3. Okay, so this honestly breaks down a lot of the different sections within Uniswap. Range orders, and we're not going to map all of these, but it's good to kind of see where it's all included. I think I'm going to start from the core and periphery repositories from the jump. All right, so we have our actors. Let's get some more text in here. We have developers. We have users. We have, oops. I wonder if, yes, we can do bullet points. Okay. Let's go ahead and change this to bullet point list. All right, I got this first one. All right, perfect. some fugly looking box, but it's okay. We're just doing this for simple visual purposes. So we have our actors, we have developers, I hate to have to deal with formatting for this. Okay. All right, so actors, and I meant to say users. Developers, we have attackers. We have liquidity providers. So when you think of this, you need to think of all the different ways these actors are using this protocol. That can help you visualize what exactly is happening, but it's also best to help you visualize maybe some gaps. If you're looking at the liquidity provider happy path, you may say, okay, it looks like the liquidity provider deposits, I don't know, 5 tokens, they're supposed to get this percentage. Well, an issue that can arise is, does the liquidity provider get the percentage that they're supposed to? Or can the liquidity provider somehow get more percentage than they're supposed to? So that's actually an attack vector. I didn't even have to see or go, I didn't even have to have the visual diagram to already come up with those attack vectors, but now that can help us create some attack vectors, but also a visual diagram of what's happening. So I know I said I wanted to pretty much start with core, what's core and periphery. So we can title something like core contracts, and we can title something like periphery. And we can say like the core contracts reference periphery. We can write what is that relationship in here between the two. I might also do some interesting things like a sticky note that kind of explains what the core contracts does and what periphery does. We may want to include some subcontracts within the core contracts. So I'm not going to do all of them, but let's look at this core repository. Maybe the description, power of the protocol, contracts. Okay, so we have a factory, pool deployer. Those are just some small pieces. Pool deployer. And you can adapt this to however you like. This is how I threat model. This is how I kind of see what exactly is happening. What are all those connected pieces? I'd have more notes. But you can see how this is built out, where you can understand all the interactions that's happening, who are the actors, what are the different assets, which reflect these. So now we can enter in our assets field. I should probably space out these a little bit more. So we have, what are our assets? First off, we have a website. We have smart contracts. If I want to dive deeper into some of the smart contract assets, would have factory, pool deployer. We have periphery. You can represent these however you like. And you notice I put website because there are also Web2 portions of this architecture that you want to include. That's if you are doing, a full holistic security review. If you're just focusing on the smart contract auditing side, this is really what you look at the contracts. All right, so let's look at some attack vectors. And I'm going to bring this down here. I'm going to copy one of these. And actually, Don't need the rest of those, just the top. Okay. Let's maybe look at where the liquidity provider would interact with, since we kind of thought of some simple attack vectors. Pool. Is there a liquidity provider? I don't want to spend too much time going into the code. Okay, modify positions. This is a private function. Trying to see if I can find where the exactly liquidity provider is. Okay. Let's go here. Liquidity management. Okay, so that's here. We're not going to jump too deep into this, but it looks like this is where liquidity management is happening. All right, there we go. Yeah, the add liquidity. So we already can see that the periphery is what handles the liquidity portion. So we have liquidity providers. Let's think of an attack vector for liquidity providers. We may have, that contract was called non-fungible position manager. I'm gonna do a short title for that, so just position manager. All right, so we know that an attack vector here, and what I typically like to do is throw like a little X, see if they have that. Let's look at some shapes. All right, if not, I'll just do text. And I'll throw in that X emoji just so I know the the attack vector. Also don't want to get too deep into this, but typically you have some type of labeling system for your attack vectors. So like I may say like LP A1, LP attack vector 1. So I know that it's the liquidity, the actor is a liquidity provider, and it's the first attack vector. And then I can throw that here, and then in my attack vectors section, I can literally say LP A1, and then write what that is. So now whenever I go back and look at the attacks at the end of this audit, and let me zoom in, I'm over here. toasting some people's eyes. Okay, so all right. So that's as big as it gets. Sorry, the visual is not that great in VS Code, but I just like having everything in one place. So yeah, LPA1, and you may say potential vector, or say potential vuln where liquidity provider receives too much in exchange for liquidity. So that's one potential attack vector. Another would be A2, potential vuln where liquidity provider cannot claim their liquidity. Oops, not their liquidity, their rewards. Okay. That's just a simple, two simple attack vectors that I could come up with off the bat. And these may not be the case, but when you threat model, you want to have an understanding of the actors, assets, potential attack vectors, and also how this architecture looks. That way, when you start looking at the code, you can validate if these potential attack vectors even exist. And this is also good for someone who is a developer, because you can do this before you actually code and build out your project. So there's two benefits of threat modeling for not just the developer, but also for the auditor. So I'm not going to jump more into it. This is a very simple view at what one of my threat models would look like. Obviously, whenever I go through this exercise, it's much bigger. There's a lot more attack vectors, there's a lot more assets and different actors, so it's definitely fully flushed out. But what I wanted to do was kind of take you through my thought process of how I would perform a simple threat model. All right, so in Module 2, we're going to talk about some common vulnerabilities. First, we're going to start off with vulnerability research and just resources you can use whenever researching about vulnerabilities. Next, we're going to talk about the re-entrancy attack, then incorrect math, a little bit on Oracle manipulation, some logic errors, and then we'll finish off with access control. So many people wonder, where should I start when looking up vulnerabilities? And then also just doing some more research on these vulnerabilities. The first thing to use is demystifying exploitable bugs in smart contracts. This is a research paper that we believe you all should read. While it's not a homework assignment, this is something that you're going to want to read. It's a great research paper on looking at some of the different vulnerabilities in smart contracts. Another resource is using DeFi Hack Labs. They do a lot of different tests and simulations for hacks that have actually occurred in real time. So what that means is, if there was a big hack in 2021, DeFi Hack Labs likely has the replica of how this hack went down, as well as some tests for that. So you can look at it. They have some data on how much was lost, some tweets associated with those hacks, and then also some Foundry tests that kind of go along with what actually happened. And then in terms of newsletters, you're going to want to look at BlockThreat and Rect. These are two great resources for just understanding what has happened in the week, or just keeping yourself up to date. These are some of the best resources you could use, honestly, for your vulnerability research, understanding what attackers are doing, and just getting a better handle on their techniques. Okay, so next is the common re-entrancy attack. It's very, very popular, very common. We have talked about this before at a high level. We're going to do another gloss over and go a tad bit deeper. But this is what essentially was used in the DAO hack back in 2016 that caused the merge, or I won't say merge, but that caused the transition, the fork from ETH Classic to what we have today. So similar to a recursive function call in programming, this is how the re-entrancy attack operates. I know we have a diagram here, so if we look at contract A, this is where your original logic is. And then if contract A were to send funds to contract B, we can have a trigger, what we call this fallback function. We can use that to call back into contract A before this contract A's function has finished. So essentially what's happening here is we have our check balances, we have our send funds. This is what gets sent to contract B. Update balances has not happened yet. And contract B can call back into this. And so as you can imagine, we can call into send funds, a nested however many times you can to extract money out of this contract without an update to the balance. So we're going to walk through an actual example later on in this session. But that's the best way to look at a reentrancy if you are, a Web2 developer and you're familiar with a recursive call or calling back into a function. Just some more semantics. It's called a reentrancy attack. I think of it as a function re-enters. It re-enters back into the original calling contract. We'll talk more about mitigation strategies, but the best way to counter a reentrancy modifier, this is for developers and security auditors who need to know this, is to use a reentrancy modifier and or the check effects interactions pattern. It's best to use both. Reentrancy modifiers are included with, you can use OpenZeppelin's library to bring in one of those, or you can create one yourself. Highly suggest you use OpenZeppelin's reentrancy modifier and use the check effects interaction pattern. Again, we'll go into detail on how that works, but the check effects interaction is essentially like this. We have our check interaction in effect, but we would do our check effect, which will update the balances, and then we would send funds. So this is check interaction effect, and we would change it to check effect interaction. And then there are various types of reentrancy. This is the basic and most popular one, but there are things like read-only reentrancies. There's cross-contract reentrancies. There's different types of reentrancy attacks that you should be familiar with and that you will likely encounter if you are designing or building your own protocol or you are auditing a protocol. Okay, so let's take a quick look at arithmetic errors, or arithmetic errors, however you want to say it. This is essentially when you have incorrect math in your protocol, and this creates a hole or gap in your contract that can leave you susceptible to an attack. Arithmetic errors are anything involving rounding errors, dividing by zero, incorrect token decimal usage, and then overflows and underflows. Honestly, this can be anything revolving around bad math, bad numbers. That's the best way you can think about this, or that's the best way you can classify these. Just to kind of talk a little bit more about each of these, think of a rounding error and how this can be bad, a bad case for money. Let's say my contract or program rounds down and doesn't send someone the full, let's say the full 22.3 ETH, and it just sends them 22 ETH. They are essentially missing out on 3 ETH. That is a bug. Dividing by zero, if you have a situation in your contract that divides by zero, you'll get essentially an undefined answer. You're not going to be able to actually do this. This is something that will create a bug within your contract. Next is token decimals. Depending on the token type, Let's say USDC, for example. USDC has 6, I believe, token decimals, and then ETH has 18 token decimals. So if you hard code the token decimals in your contract, and let's say you accept one token, let's say USDT, but then you try to accept USDC, are those tokens going to be, is the token decimal going to be the same? So if one of those has 6 decimals and one of those has 7, you could be potentially giving someone $1,000 more, or they may not be getting their correct amount of tokens. So this is a very important topic, that you understand how to properly implement token decimals within your contracts, but it's also important that you can spot these types of errors. Next is overflow and underflow. Depending on the versioning of the Solidity Pragma, this can definitely vary. I believe after Pragma 8.0, these overflows and underflows are already protected within your smart contracts, as long as you had this Pragma, this updated Pragma. Anything before that would essentially overflow if you were to add a certain amount of numbers that's higher than the actual storage available. But also, I wanted to say that just because you have the latest, or you're using the latest version of Solidity, you can still have overflow errors. If you try to essentially increment or decrement past a level that your type allows, this will lead to revert or reversion error, and this can lead to all kinds of denial of services. So just because overflow and underflows are protected against, this does not mean that you won't be able to have an overflow or underflow error. This can still change up how your contract is impacted if you have these kinds of issues. Okay, so next is oracle manipulation. When protocols are relying on oracles, they automatically execute actions even though the oracle provided data feed is incorrect. So essentially, we know that oracles are when you bring data off-chain, on-chain. And if you're relying on oracles to automatically perform actions within your smart contract, this can become a huge issue if this oracle is not correct, right? This is something that you as a developer or a security auditor have to watch out for, because what if that oracle feed is wrong? If you are getting incorrect token conversions, your protocol may be giving more tokens than it should, or it may not be giving as much tokens as it should. So this is something that you must pay attention to if you're implementing an oracle. There's all kinds of security checks you're going to have to include. Also, a classic vulnerability comes from trusting the spot price of a decentralized exchange. The reason why this is an issue, for those of you who are not familiar with a spot price, is the price can drastically change in a matter of time. Let's say we took a 1 minute time span. If I wanted to, I could manipulate this price by taking out a flash loan, essentially inflating this price, and then making some kind of move based off of this artificial change. And while it is, I won't say it's artificial, because it actually is a change in price, but sometimes contracts may not react appropriately in times where the spot price or the price has changed drastically. So it's best to use time-weighted average price. That way you can protect yourself against these oracle manipulation types of attacks. We can go deeper into this in our study halls if there's any questions. There are plenty of resources out there for understanding this, but we just wanted to make sure we introduced the issues with using oracles, but also some things you need to look out for when you're auditing your protocols or when you're developing your protocols. And if you're a developer or auditor, the best thing you can do is look at that time weighted average price oracle. That's TWAP. Look more into that, do some research, and you may want to decide if a spot price oracle or time weighted average price oracle is best for your protocol. Okay, next we're going to talk about unchecked returns. So it's a really huge issue that protocols miss this easy vulnerability. So some protocols fail to check the return values of functions. This is a huge problem because many developers assume that a function works a certain way, but they don't necessarily understand what is actually happening behind the scenes when that function is ran. And the way you can mitigate these issues is by using backstops or requirement checks. It's just a way for you to handle this logic if you don't get the result you expected in your code. So let's take a look at this small example. We have a payment function. It's requiring that paid is false, and if it's not paid, then we are going to pay somebody, right? So what's happening here is the developer has assumed that the send will go through. They have not made an alternate path to handle this return value. So this send is going to return true or false, but paid is always going to turn out to be true no matter if it was sent or not. So essentially what can happen is I can pay off a debt or pay someone, and the contract will say, perfect, you have made your payment because we did not check if the receiver actually received the money or if it went through or not. We have automatically assumed that once we get to this line of code, the contract will send my payment. So like we said, what you can do is use a requirement statement to assess what that return value was. Now, this is not a huge issue in terms of return values for your own contracts. As a developer, you will typically have some checks for this logic because you wrote it and you're familiar with what's going to be returned. But where this gets a lot of developers is when you use outside libraries where you haven't necessarily read through the documentation in detail or tested this logic in detail. And you may have only tested the happy paths of this being sent. But if you were to do some more tests, you have seen that, okay, there are cases where a payment should have failed, but it didn't. So this is something that's very important for both developers and auditors. As I'll continue to say, developers, just make sure when you are using different libraries or forking other people's code, you want to make sure you check for these return values. And then as an auditor, if you see external function calls that are being made within the contract, check and see what does that thing return. Make sure you're testing this contract and you're stress testing it to make sure that if there is a situation where there's a failure, has the developer handled that situation correctly. The last slide in this module will be on access control. Access control vulnerabilities exist when a contract fails to properly restrict who can call certain functions. This can result in unauthorized function calls. So as you all learned, whenever you're making various calls within your smart contracts, it's really important that you understand who can call these functions. We talked a little bit about threat modeling and the different users and the actors in this process. So you have the developers. They should be able to call certain functions. You have users, they should be able to call certain functions. You may have privileged users, they should be able to call certain functions. You may have, another admin tier like routers or controllers. All of these different actors are going to have various forms of access control, and you're going to want to make sure that that is only specific to them. A basic user should not be able to call a function that a developer can. Another interesting way that access control vulnerabilities can be introduced is you may have specific conditions that need to be met. If it's not role-based, you may have condition-based access control. Well, you need to make sure that a basic user um, that shouldn't be meeting this condition cannot meet this condition. So this is something that is seen in many protocols. Even if you are an expert developer, you will likely create an access control vulnerability. It just happens. But this can be mitigated by doing reviews, um, by having auditors do reviews for you. So we won't jump into that just yet. I'm going to go down the rabbit hole. But let's take a look at this example token functions, or this token contract. So we have a mint function, and then we have a burn function. And as you can see, there's proper access control on this. I actually got this from OpenZeppelin's access control documentation, where you have a role, you have a minter role, and the sender has to be this minter, or they have to have this minter role. If they don't, they cannot mint. They cannot mint this token. Same for a burn. If the message sender does not have a burner role, they cannot burn this token. So it's best, honestly, to use some of OpenZeppelin's libraries if you want to create some solid access control that's already kind of built in for you, and you don't have to bother with trying to create your own logic that may be vulnerable. It's best to use other libraries that are battle tested, and OpenZeppelin's access control vulnerability library is actually pretty good. So this is a small example. Later on, and when we're doing code reviews, we'll probably encounter an access control vulnerability.
Now we're going to shift focus to talk about how protocols and protocol developers can defend themselves and proactively make sure they have good security and good security practices, both for their protocol security, but also their users. I'm going to talk about code architecture. So that's when, before even building the code or when adding functionality, what is the design of the software that's being made. We're going to talk about the development process for the protocol and some best practices. So that's things like if you're working with a team, if you need credentials for things, like how do you safely store those? What are the practices for merging code and then deploying that code in a safe way? We're going to also talk about tests, where testing fits into this, and the different type of tests that can be used to help make sure protocol is secure. The next point we're going to go over is security reviews, and how they fit into the whole process, not just a one-off security review. Then we're going to talk about bug bounties, how they're also very helpful for securing protocols. And the last piece is we're going to talk about circuit breakers, which is technically a part of code architecture, but I think it's important enough to deserve its own section. This session was inspired by a article written by Trust. If you're not familiar with Trust Security, Trust is one of the top security researchers in the world, and Trust Security published this really good blog post that I encourage all of you to read, talking about the different ways that protocols can protect themselves. As developers are writing code, usually protocols we use GitHub or some other type of version control software to manage those teams, to make sure that code is being added efficiently and there's a centralized source for that. In terms of this development process, it's important to have a good process both for developer efficiency but also security. The first point is having guarded policies with pull requests to whatever main branch is being used to deploy the protocol's code. So it shouldn't be possible for anyone on the team to force push code to the main branch or to run the production deployment pipeline. It's good practice to have a pull request review strategy, such as requiring certain develop at least one approval from certain members of the team, or requiring multiple approvals. Uh, it's also good to enforce test passing per pull request, and also having what's called good test coverage. Or test coverage is given the code that's in the system, how much of that code is being actually executed during when you're running tests. Another important point with the repo management for protocols is how you manage any secrets that you may use. So that could be API secrets, private keys for wallets, and how those are stored and who has access to those. Another point is for the developers themselves working on the code, making sure they have two-factor authentication set up just in case, their username or password gets hacked. They're still able to not the attacker wouldn't be able to log into their developer accounts with two-factor authentication. Another point is I like to think about it from coming from a place of the least privileged as possible in terms of permissions. So if someone only needs read access, just give them read access to something, not read and write, just because it's easy to give an admin credential. Another point is it's very important for developers and protocols to be continuously learning about pitfalls, security pitfalls, different hacking techniques, and the latest exploits. Like Miles mentioned previously in this session, I like to use newsletters and also YouTube and Twitter, but the Block Threat newsletter is a great way to keep up with the latest security hacks and best practices and research. It gets published once a week and it's fantastic. Couldn't recommend it more. And the last point is security should be top of mind throughout the entire development process. So even before a line of code is written, when the protocol is still being designed, security should be top of mind, thinking of what entities should be able to do what, and just always having some attacker mindset looking at the protocol. The next aspect of how protocols can harden themselves to minimize the risk of being hacked or exploited is test. As with Web2 software, tests are very important to validate the software is doing what developers expect it to do. But it's also important to validate security aspects as well. So aside from what I just talked about with best practices for merging code into a main branch that a protocol is using, it's best practice to enforce running tests on every pull request and make sure the test passed, and then also enforcing some type of minimum test coverage so that as code is added to the protocol, you can make sure that tests are being written. So if tests aren't written, then the pull request won't be able to merge. Outside of just writing good unit test, and if you're not familiar with the unit test, a unit test is when you're testing something in isolation. Usually it can be something like you have one smart contract and you just want to test one function inside of it is doing what it's supposed to do. The next level up from that are what's called integration tests, and those are used for testing testing smart contract interactions. So if you had a contract that was calling another contract, uh, that would be considered an integration test. There's also another class of tests called fuzz test, which we won't get much into, but those are very helpful as well. And the last point here, there's another type of test called invariant test. So I think just understanding what invariants are is very helpful when thinking in terms of tests, but also in building a mental model of protocols. Because I believe if you're able to think of protocols from the invariant perspective, it'll make it a lot easier for you to understand how it works and then find ways to break it. So to explain invariant testing, first I want to go through what is a protocol invariant. And to do that, I'm going to borrow this tweet from Seraphin Audits. Great follow, by the way. They post a ton of great security knowledge. They do audits. They also run a bug bounty platform called CodeHawks. And they work with SolidityATL as well, which is a great tool. So what is an invariant? An invariant is a property of a system that should always hold. For example, in a lending pool like Aave, the invariant is that the protocol should always have more collateral than debt. So that's an example of what an invariant could look like. You can also have other invariants, such as if you have a vault, users should only be able to withdraw. They should be able to never withdraw more than they put into the vault. That's another invariant. And a part of that invariant testing is writing tests to validate those invariants. So that's another class of tests that are very powerful in making sure protocols are secure. The next thing we're going to talk about for how protocols can defend themselves from being attacked are audits or security reviews. This is one of the main responsibilities of security researchers. And firstly, audits are a continuous process. So protocol should not just get one audit and be done, because an audit is a snapshot in time. And depending on the time the auditor has, and also the number of vulnerabilities that are found, that can influence the quality. For example, if an auditor finds 5+ high or critical vulnerabilities, and the scope of the audit was 2 weeks, there could be a chance that there's more, and they just didn't have time to find more. So protocols generally should have a continuous audit process as they're building. The different types of security researchers that perform audits, some protocols have internal security reviews, so they'll actually hire full-time a security researcher or security engineer to perform internal audits. There's also solo auditors or small firms, which are an emerging type of audit that's a cheaper alternative to the larger firms. There's also the larger firms that perform audits, and there are audit contests where it's public audits on platforms like Code4 and Sherlock. Generally, it's good to have audits before deploying to mainnet, and having multiple audits is also recommended. So maybe it's having an audit from an internal security review and then audit contest, or having a solo auditor do one and then a firm, or having multiple solo auditors or smaller firms do it. Once the protocol's code is actually deployed, it's also best practice to open up some type of bug bounty. That means that white hat hackers will have the opportunity to look at your code as it's live and report findings they have. The last piece is also thinking about the Web2 security practices and making sure that's involved in your security view. So if you have, some back-end code or front-end app that's interacting with the contracts, that's also something that should be included in audits. As I mentioned when talking about audits, once a protocol has deployed their code to mainnet and it's live, they should create a bug bounty. Some of the platforms for that are the first one is Immunify. So this is a platform where projects can come and post bounties where white hats can come and report vulnerabilities to get paid out. It's the largest Web3 bug bounty platform. Yeah, another platform is Hack and Proof, which is similar, but they also have a lot more bounties as well for the non Web3 components of the protocol. Oh, bug bounties are fantastic for a few different reasons. So one, they provide an around the clock coverage because there will be motivated white hats spending their time looking for vulnerabilities in the code base. It's also good that they are public facing and the protocols who are creating the bug bounties get to define the payouts and the conditions for what they'll be willing to pay for. And it does give a little bit more confidence if a protocol is willing to post their code open and publicly so that other people can try and hack them and report those. It is a great deterrent for black hats because one of the challenges of black hats is once if they were to actually perform a hack, it's very easy to track the addresses as they try and actually get that money off chain. And so bug bounties offer an incentive to report the hack. And generally for higher hacks, especially for criticals and highs, the payouts would be around 10% of what could have been taken. So if someone found a vulnerability that could have taken $10 million, they'll get paid out $1 million. So what we're looking at here are the open bounties on Immunify. You can see you can sort these bounties by different aspects, like when it was last updated, how much they've paid out. And if we were to look at one of these, one thing to note is a lot of the bug bounties don't require KYC. So white hats will be able to just provide their Ethereum address to receive payment if their bounties are found valid. Generally, in terms of a structure of what makes a good bug bounty posting is having a good high level description of what the protocol is doing, linking to the website and documentation like Yearn Finance does here. Also having a clear breakdown of the different levels of vulnerabilities. And we're going to talk about these levels once we start diving into audit reports. But the payouts are usually defined in what tokens they can be in. Generally, there's USDC or that protocol, or some other stable coin or that protocol's token. And you can see based on the level of the vulnerability, so low, medium, high, critical, there's different payouts. And you can click on Immunify's classification system to see how they actually define those vulnerabilities. And it's very important to understand if you're looking for bounties, what is defined as a medium or a high or a low. And then having a good list of the actual contracts that are in the scope. Generally, if you were to click on one of these, it's best practice that these contracts are verified so that white hacks can actually read the code inside of here. Because if it's not, then it makes it a lot harder for white hats to help secure protocols. And let's see. Yep. And then there's also, it's important to have a good section detailing what submission requirements are. So, do you require proof of concept from white hats? What other things do you are needed? And the protocols themselves get to define the impact. So this is how Urine Finance describes a critical, and they do the same for highs, mediums, and lows. So this is an example of what I would say is a good bug bounty post. The next aspect of how protocols can defend themselves and minimize the risk of getting wrecked is the code architecture or the protocol architecture. So this is from how the actual protocol is designed. And this goes more into the software architecture aspects, not necessarily the implementation. So as with writing code, when designing the protocol architecture, security should be top of mind the entire time. So thinking about permissions of who should be able to access what, um, designing a protocol in a way where it's as simple as it can be, because generally complexity will add more of an attack surface. And also recognizing that your first iteration of designing or architecting a protocol, you're going to have to iterate on it. And during those iterations, you're going to be learning more about the assumptions you made when you designed it. And so you want to make sure that you're validating those assumptions and always keeping in mind if this can be done simpler, uh, because generally complexity introduces more bugs. While designing a protocol, threat modeling should be a part of this process. So not only drawing out all the bits and pieces of what should go into specific smart contracts or what type of database you're going to use, should also be a threat model of here are the different actors in this protocol, here are the permissions they have, and here are the things they can poke. And here's how the fundamental trust assumptions, um, just so that there's no being caught by surprise. And the last piece is using established Solidity design patterns. For example, when upgrading contracts, there's tested, proven ways to write securely upgradable contracts. Those type of design patterns have been learned by the Solidity community. So reusing those patterns can help you, one, not have to think too much about it, and two, have some confidence in the security of the way that it's done. What we're looking at here is a simpler version of an architectural diagram showing an entire system. So starting all the way from the back end on chain, there is, you can imagine a lot of protocols can be drawn like this from a high level, but there is some on-chain component and smart contracts. There may be oracles feeding data onto that chain. There, those smart contracts are running on nodes. There could be some front end system interacting with either directly with smart contracts or through some other backend services. You can imagine these backend services being a Node.js server or a Rust server that can communicate with a smart contracts, or they may just be talking to a normal database like Postgres or something like that. And then users are interacting with this front end generally through a browser over the internet. Um, and the user can be interacting directly through the browser, or uh, they could just be a wallet. So there's not that much information about them, and that wallet's what's interacting with the front end. So this is an example of what a high-level architecture of protocol might look like, and each of these pieces can be stepped into and have a lot more detail on inside of it. One subset of protocols architecture that I want to touch on is a concept called circuit breakers. So a circuit breaker is a software architectural pattern to minimize the impact of hack. And so some examples of that would be pausing a smart contract, where if a hack is discovered, having some type of automatic pausing of contract, for example, to freeze liquidity pool if someone is starting to steal funds. Because a lot of hacks actually occur over multiple transactions where someone's running an exploit multiple times to drain as much as they can. And so pausability through a circuit breaker can help some protocols make it so that maybe that first transaction works, but then subsequent transactions don't. So to highlight that, I don't want to spend too much time on circuit breakers because it is a somewhat advanced concept. Consensus, I think, has a really good breakdown if you're interested in learning more on what a circuit breaker is and how protocols use them to defend themselves. I would also recommend just this resource in general because you can see there's a lot of other patterns that they write about and talk about the pros and cons of. So the circuit breaker is one common pattern that's used to minimize risk of all funds being lost in the event of a hack. I didn't include this in the module in module 3's opening list, but I think it's important to talk about. So the last piece on how protocols can defend themselves from hacks is insurance. And this is something that is relatively new in the Web3 space. I've only been seeing this for maybe a year or two. But the two examples I want to go through are Sherlock, which is one of the top Web3 open audit contest platforms. Sherlock they not only perform audits, but they allow for some insurance coverage. And they're set up to offer up to $5 million in reimbursement for protocols that are audited on Sherlock in the case of a hack. And they also provide some funds for those protocols to have a bug bounty. So here's an example of them actually paying out from that fund. So a protocol that was hacked that had a contest on their platform, they were hacked for $1 million. The hackers actually returned 90% of it and kept 10% of it. And Sherlock was able to pay out 75% of the remaining losses there from their claim. And you can see here what that was. The other insurance protocol I want to talk about is one that Sherlock actually partners with called Nexus Mutual, sorry. And their entire purpose is for protocols to have some type of insurance in their assets. So insurance is an emerging market in Web3. I think it's very much needed. And so there are some ways for protocols to have some insurance in the case of a hack.
This last module, module 4, we're going to do a vulnerability deep dive. So we're going to look at a re-entrancy attack in depth, as well as an example. And then we're also going to look at an incorrect math attack in depth, as well as an example for that. All right, so in this module, we're going to go through a re-entrancy attack example, and we're going to look at the Stars Arena hack, which resulted in about $2.9 million lost. Also, there's a read-only re-entrancy attack that happened with Sentiment XYZ, which resulted in about 500K lost. We're not going to cover this in detail, but you can use the links we post to you all to follow how this attack occurred. So the other day, Stars Arena was attacked due to a re-entrancy hack, and we're going to show you how you can follow along with DeFi Hack Labs to see this attack in action. So you're going to want to first go to this link here, and we have some details on this hack with link references as well as the exploit contract. You're going to want to make sure you clone this repository. So go ahead and clone this down to your computer. And once you get there, you open this up in your code editor and you will make it to this. This is the DeFi Hack Labs repo that I have pulled down. So let's look up Stars Arena. And thankfully, they already set up everything for you. So all you have to do is run forge test that they give you, this command they give you. And let's just take a look at the Stars Arena exploit for just a second. So as we know, a common re-entrancy attack happens when we re-enter into a function using some type of fallback method to exploit the victim for however much funds we can. So this is an example where Stars Arena actually is pretty close source, but apparently they forked from Friendtech. So they forked and I guess made some small edits or changes that they shouldn't have, and it resulted in this attack. So if for those of you who are not familiar, the flow for a Friendtech or like SocialFi type of app is you can buy shares that represents like an individual's account. So like, let's say if it was my Twitter account, you can buy shares of my account essentially. And then, depending on my social score, if I gain a lot of followers, people like me, I start getting more shares, then essentially those earlier followers will make a profit off of my growth. So you can also sell those shares and, like I said, profit off of this. So what the attacker figured out was a way to re-enter into the contract where when they sell the shares, they actually get more shares than they should have. So that's kind of like the overflow or highlighting how this attack happened. But let's look at the code to see what happened from an exploit contract perspective, since we don't have the victim contract code itself. So we're dealing out 1 ETH to set up this attack. This is the attacker's balance before. So they call the contract. I'm assuming they're doing something where they're buying shares of some sort. If not, maybe they've already bought shares to set up this attack. But they're supplying this contract with a value of 1 ETH for this function call, which we don't really know because Stars Arena is closed source. So this is how we reconstruct this contract. We can see the bytecode and what happened on chain, and that's how you can recreate this attack. They have a requirement check just to make sure this passes. They have a second call to sell shares. And then at the end of this, the attacker balance after the exploit is displayed. And here's the important part where the re-entrancy attack actually happens. So as we discussed before, usually there's some sort of fallback function that your exploit contract will call to allow you to re-enter into an open function call that you already have. So again, maybe I need to come back to this visual. Let's come back for a second. Do we have a re-entrancy here? Yes. So remember, you have, let's say this is the Friendtech, or not Friendtech. Let's say this is the Stars Arena contract. This is my attack contract. So similar method. We have some calls. Clearly, we don't know what those calls look like, but we have this function call and we have this sell shares function call. So we have these calls, and then it does something where it sends funds into my attack contract. So let's go back. Funds are somehow being sent. I'm assuming when we sell shares, once we sell those shares, we receive this value of some sort, and because of this logic, once we receive funds, we re-enter into the Stars Arena contract, which allows us to then further extract some more money. So that is essentially a re-entrancy attack outline, and we can see this same structure being followed. So this is a great example for if you don't have the source code, but you have the on-chain interactions, which allow you to kind of see what essentially happened in this attack. And let me pull up one quick example before we look at that code. Falcon Scan is actually a great tool to trace transactions. So even if you don't have the code, you can see the call stack of what happened. And the call stack for this attack showed an attacker re-entering into the Stars Arena contract, which further resulted in this exploit. So let's look at, let me clear this. Let's look at this test. And what we're going to see is the balance before the attack here and the balance after the attack there. So the attacker ran off with some pretty great profits. What I like to do is throw in an extra V right here, which allows us to see the call stack, similar to what we saw right here with Falcon Trace. Okay, and while these aren't labeled as great as Falcon Trace, we do see the flow of how this attack happened. So we see the attacker being dealt their one AVAX. This is the log that's emitted up here. This is where we are in the code. You see some type of function call is happening, which sends about one AVAX to the victim contract. Then you see our contract actually does receive something here. This is where the exploit starts. So the exploit starts, our receive function is called, and something is changed. And I believe when looking at some of the attack breakdowns, it was actually modifying some variable that allowed the attacker to toggle how much the shares was worth before they actually sold it. So following that logic of what I was reading plus the call stack, it's showing that something was toggled in this receive function down here. This caused a change in the stars reading contract, and then when they sold the shares, they received a fairly large value of AVAX. And then, yeah, to finish it off, the attacker's balance after this exploit was this large value they got from the re-entrancy attack. So this is a great way to visualize an attack, even if the code is closed source. There's a lot of information you can extract from the on-chain data itself and still evaluate this attack. Even if you don't know the exact details of what's happening, you can see maybe the kind of attack that they used, but also what was vulnerable. And we clearly can see that there was something vulnerable in the logic for selling shares, as well as whatever function they called that allowed them to re-enter. So we're going to look at how they could have maybe prevented this. So we go back to our presentation. Let's look at how a re-entrancy attack can be mitigated. So first, you can use the checks, effects, interactions pattern. What this does is, like we kind of mentioned before, whenever you perform some type of action, let's say you want to make a withdrawal, if you first provide a check in the beginning of that code, and we're actually going to look at an example. First, you provide a check, then you do whatever is supposed to happen. Then you change the logic within your contract, and then you do the interaction of making that withdrawal. Similar to this checks, effects, interaction, there's also the functions require, effects, interaction, protocol, and variance. But also you can use a re-entrancy guard. So let's look at these two, because these are actually fairly similar. The only difference really is the invariance. So Patrick made a great post about this very thing here. And let's look at this example. So we have our withdrawal. We have our check, which we want to withdraw, so there's got to be some type of balance. We're requiring that the balance of that sender is greater than 0, so we don't want someone who doesn't have any stake within this protocol to be able to withdraw, so that's a check. We have our effect. So even though we did not send the withdrawer their funds yet, we already need to change their balance to be 0. The reason for this is because of re-entrancies. If we make sure that their balance has to be greater than 0 right here, they can't re-enter once they have make their first withdrawal. So that's why this pattern is needed for at least smart contracts dealing with Ethereum. And then next we have our interactions. So this is where we actually send the user their withdrawal money. So, in a typical flow, you may think, oh, I can check the user's balance, then I can send them the money, and then I can make their balance 0. But you just have to reverse these two around to make sure that you prevent re-entrancy attacks. So that's the check, effect, interaction pattern. But this other method, the function, require, effects, interaction, protocol, and variance, I would honestly label it checks, effects, interactions, and variance pattern. But in this pattern, the only difference is we have a protocol invariant. So this is a great programming pattern to make sure, even after you have checked for something, from a look at your whole protocol, is this logic something that should actually occur? So in this invariant, we want to make sure our total balances is greater than 0 after this withdrawal has been made. So if the attacker were to somehow bypass these, this require statement would reject this attack, because the protocol invariant was broken. So this is a great pattern. There's a lot of controversy around, oh, it's like extra gas using all these require statements and these checks for the invariant, but at the end of the day, you make your protocol much safer when you include invariants into your programming logic. So as auditors, make sure you are properly checking for these and letting developers know about this pattern and what they can do to fix their re-entrancy attack. And then as a developer, if you're taking this course, use protocol invariants within your functions to give yourself some extra security while you're developing. And then Patrick goes on to say a lot more about this, so you can read this thread. We'll be sure to link this as well. And then lastly, you can use a re-entrancy guard. So I know we talked about this, but let's just take a look at this code. So here's a re-entrancy guard. And essentially, when you include this in your contract, you use this non-re-entrant. This basically allows it prevents someone from being able to call back into itself. So, well, it says it right here. Prevents a contract from calling itself directly or indirectly. So if you inherit this Open Zeppelin reentrancy guard contract, and then you place the non-reentrant modifier on your function call, then no one will be able to re-enter into that because of this modifier. So that's something you can also do. It's another great method, but personally, I would say use all three of these. Just rather be safe than sorry. Maybe that's overkill. I'm a security guy, so that's why I say to use all of them. But you can kind of choose whichever you need for your function calls. In this last slide, we're going to go through an example of using incorrect math in a protocol. So we're not going to go through beauty chains, but essentially what happened here was the protocol devs use a Solidity version less than Pragma 0.8.0, which does not automatically check for underflow and overflows. And this is essentially what happened. If you're not familiar with overflows, this is when, depending on the type you're using, you can overflow those values and those numbers would wrap around essentially like an odometer. So let's say we use a type that goes only up to 10. Well, if I add 1 to the 10, it would wrap around, excuse me, it would wrap around and start back at 0. So obviously this is not something, it's not like overflowing values would work with examples of 1 through 10. But for instance, if you're using uint type 8, that means you can only store to the number 255, and if you add 1 to 255, then that wrap around back to 0. So when you're using Pragma version 0.8.0, this automatically is checked and a revert would occur, your program would stop. This is a lower level vulnerability that we're not gonna run through. I gave a quick run through or overview of this, but we're not going to show an example because this is something you can see everywhere in terms of different examples, and this is a pretty easy one to understand. We'll have resources for you to look at that if you do have some issues trying to understand how overflows and underflows work, and we'll also go through them in study hall. But what we want to focus on today is a precision loss example. This is a little bit higher level, and this is something that you all should be looking at and studying in detail because these are more prevalent in the code you'll find or the code you'll be reviewing. So we're going to look at balancer phi's rounding error that happened, there we go, August 27th. So let's take a look at this contract. We already have it cloned down. Okay. All right, so when we look at balancer contract, or the balancer exploit contract, there's a lot of things going on over here. there's going to be some swapping going on. There's going to be a flash loan being used. So this is a really great example for understanding a higher level bug and how they can be exploited, because it kind of uses some of the standard approaches that an attacker would make to hacking a protocol smart contract, somehow using a flash loan to inflate some price in some way, and then exploiting that by withdrawing a huge amount of money. So we're gonna just do a high level walkthrough of this, of what's happening. So to give an overview of the exploit, there's essentially a rounding down error that leads to a business logic flaw. And if you're not familiar with rounding down, if you were to, let's say, divide a few numbers, and you end up with 1.5, for example, if you round down, that would be 1. If you round up, that would be 2. So depending on which way you round down or up, that can determine the logic flow of your contracts, right? If you round down, that can change how much your users are receiving. That can change some internal logic. If you round up, that can also change how much your users are receiving, and that can change or affect internal logic. And I believe when amounts are going out, they round down. And the reason I guess that they're doing this is because you wouldn't want to round up and have your users receive more money than they should have. So I guess to be safe, they round it down. Don't really know the design decision there, but they are rounding down nevertheless. So what's happening is they're rounding down, but as a result of rounding down, they're adding liquidity to another pool. And when you increase the balance or add liquidity to another pool, this can change the rate of that liquidity pool. That can change what the other token is being swapped for. So in this example, BPT is used to swap for USDC. And when they round down, this increases the balance of BPT. This is basically the same thing as BPT. And like I said, it's adding liquidity to this BPT USD pool. And I don't think they intended to do this as a result. I think they just wanted to round down, but somehow they are rounding down and adding liquidity as a result of that. And so that affected the rate of something else when it wasn't supposed to be affecting that thing. And so what the attacker did was they took out a flash loan, because they noticed this rounding down effect actually did an unintended effect on something else within the protocol. So they took out a flash loan. They performed a few swaps. Because this rounding down happened on such a large value, because they took out a flash loan, the other token was essentially the incorrect price. It should not have been the rate for that it was actually carrying. And then they were able to manipulate that. They were able to exploit that issue and drained Balancer worth of about 2 million funds. And we'll link everything so that you can go into this in-depth analysis by the BlockSec team. But we're going to just do a walkthrough of what that code looks like now that we understand what was happening here. So if we look at this Balancer exploit contract, just running through this, we have a few tokens that are going to be swapped. We have a flash loan that's going to be leveraged here. We have the Balancer tokens. We're creating a fork of mainnet, so this is essentially trying to recreate the same environment that happened when the attacker performed their exploit. We have to mirror some tokens that we're going to use in this process, and then we're going to test this exploit. So as we can see, there's these interest rate modes, and what the attacker is doing is leveraging this rounding down to change like this cached value or this interest rate, the rate for this other token. And then later, what happens is They perform swaps down here. They run off with some money, and then they repay their flash loans later on down the line. So that is the flow of this attack, and you should definitely go into this and understand it a bit more. But let's just run this from our terminal just to take a look at what's happening. So I think it said, let's go to the README for just a second. Okay. It's going to take some time because we're compiling this for the first time. Still loading. You know, there's a lot of different things happening here if it's taking this long to compile and run. So what we're going to do is cut and then come back when this says ran. All right, so we're back. So we simulated the attack. So before the attack, this is how much the attacker had. And then after the attack, this is how much the attacker had after the exploit. So as you can see, you know, this is not the same amount, I believe. Yeah, it doesn't look like the same amount, but it's just simulating the gain that an attacker is able to make when exploiting this flaw. And then like we did in the last one, throw in an extra V. Let's hope it doesn't take as long again, but it shouldn't. If we show the call trace of all of these, we can kind of get a deeper insight of what happens. So here we go. It's very long call trace. And honestly, we don't have to cover all of it here. You can kind of do this on your own. I like to do this when learning about what's happening behind the scenes, because this is essentially what it's showing what functions are being called and what's happening. So learn to use Foundry's call tracing ability, because this is a great tool to understand what's happening behind the scenes. And so you can see where, you know, there's different checks from the Aave, from the Aave flash loan that's happening. So we have our header, and then we have all the individual items that's happening underneath this initial flash loan, which takes a lot of steps. If you're not familiar with how flash loans work, it's actually a lot of steps that go into it. It's easy to do, but what's happening behind the scenes is pretty amazing. So you can see we go down where they perform some swaps. Getting at the different rate, because that's what's going to be modified when the round down occurs. Yeah, so a lot of different steps. I'm not going to cover. This would be take a long time to cover all of these, but yeah, that is what you need to understand in terms of different ways math can affect your protocol. You know, you have to put in these tests and backstops to make sure that if you're using, you know, math in some way, shape, or form, whether you're adding, subtracting, you need to test the effects of, okay, if I add big numbers, I add small numbers, what are the different effects on my protocol? Would that change a rate? Would that change, you know, how many people can withdraw? this is something that's really important, and it's an easy slip. Honestly, it's easy for developers to create math that impacts their protocol in a negative way, for whatever reason that had occurred. So let's take a look at the ways to mitigate these incorrect math techniques. Let's look at incorrect math mitigation techniques. So, as we first talked about, integer overflows and underflows used to be fairly common, but because of the Solidity progmas being updated, it's typically not a problem anymore. That used to happen a lot, where integer overflows would occur and really mess up the math of a decentralized application that's using swaps or dealing with users tokens. But Pragma 0.8.0 saved the day, so we don't have to really worry about that. But I still included that here because we wanted you all to at least understand what overflows and underflows are. This is something that you will see not only in Solidity smart contracts, but these overflow and underflows also happen with different smart contracts on different chains. Next is be wary of typecasting issues that lead to incorrect math. So if you are converting a uint64 to a uint8, that's going to cut off the amount of integers within that type, because uint64 can store a lot more bits than uint8. So I forgot how much is in uint64, but essentially you're going from billions as an integer value all the way to the hundreds as an integer value. So that's going to cut off a fairly large amount of leading zeros, or it's going to cut off a fairly large amount of that uint64 number that's being converted. So that's something to also be wary about or wary of when implementing math or converting types. And the last thing, which covers what we just talked about, was you need to make sure you test your contract using a variety of values. Because, for example, the developers of BalancerFi maybe didn't test for cases where a whale were to interact with their smart contracts, or a flash loan. They probably tested for whales interacting with their contract and what kind of effects it had, but maybe they didn't anticipate or test what would happen if someone took a huge flash loan out and swapped a few tokens. Would that affect various rates within the protocol? Would that affect any other users? So this is where testing plays a really important role in the safety of your protocol. You can use fuzz test, so you can use small values, medium-sized values, and then large values. And you can also do this a repeated number of times. You can maybe do this 100 times in a row or 1,000 times in a row, depending on how you set your fuzz test up. So these are some really important ways to mitigate these incorrect math problems. But this is just something you all should definitely have in your toolkit when auditing, and then also as a developer when developing.